Hey Gators, today I wanted to go over colligative properties and phase changes, and we have a special guest, Rose, here. So here's Rose. Hi, Rose. Okay, so to do this, we're going to share the screen. And let me go ahead and present here. Right, so colligative properties and phase changes. Now, first off, before we get to there, just a little recap of states of matter, where matter can be in liquid or solid or gas form, and it takes or gives off energy to go from one of those forms to another. So for example, if you have ice, it takes energy to get, or you have to put energy into the system to get to liquid water. And then to get from liquid water to steam, again, you have to put energy in. The inverse of that is if you go from steam to water, it actually releases energy. And then from liquid water to ice, again, releases energy. So it is a physical change when you're changing states. And either, as we said, energy is either required or given off. Now, for required, that would include vaporization or boiling something, sublimation, which is going directly from a solid to a gas, or melting, going from a solid to a liquid. All three of those processes require the input of energy. In contrast, the kind of opposite processes give off energy. So condensation gives off energy. Deposition, so the formation of like ice from gaseous H2O, that gives off energy. And freezing, again, gives off energy. So we can do a little chart here and show again. From solid to liquid is melting, and that requires energy. From liquid to gas is vaporization, that requires energy. And again, solid to gas is sublimation, it requires energy. In contrast, gas to liquid is condensation, which gives off energy. Liquid to freezing, or liquid to solid is freezing, which gives off energy, and gas to solid is deposition, which gives off energy. And the beeping is our little smoke alarm is just ran out of batteries. So actually Mrs. Cassie is getting a new battery for it, which will be fixed soon. Anyway. Now, moving on to colligative properties. Essentially, physical properties of solutions are affected by the number of particles of solute that are dissolved within the solution. Now, the more particles you have, the greater the effect. Now, because of that, ionic compounds have a greater effect than covalent compounds, because when ionic compounds dissolve, they break into multiple pieces, whereas covalent compounds break into whole molecules. And this is what you see in terms of when ice melts, or which then we'll get to it. It affects the melting point of water. It also affects the boiling point of water. Now, first off, we could ask or play a game: how many particles? Well, if you have NaCl. Now, NaCl is an ionic compound. It will split into Na plus and Cl minus ions. So it will split into two particles. Sodium acetate, NaC2H3O2. Again, it's a Na plus Na acetate minus particle. It will split into two. MgCl2. Well, the magnesium will split into one particle, and each of the Cl's will split into a particle, so it actually split into three particles. With glucose, or this is actually, glucose, would be C6H12O6. That's a covalent molecule, so when it dissolves, it will stay as an intact molecule. If we have copper sulfate, again, the copper is a +2 ion, it's a single ion. Sulfate, SO4, is a -2 ion. It's a single ion, so it will split into two pieces. Aluminum nitrate, AlNO3-3. The aluminum will split into Al3+. Each of the nitrates, there's three of them, will separate. So we'll have three particles here, one there, for a total of four particles here. Now, relating to this is a thing called vapor pressure. And it's basically the pressure exerted by liquid particles that have escaped the surface and entered the gaseous state. So what it's saying is when something, if you have a liquid and these things are moving around, some of them will escape up and be in the air and will be bouncing around, and that will be pushing down on the liquid. So there's a certain pressure pushing down on liquid at all times. Now, if you add a solute, it will then lower the solute's vapor pressure. Essentially, by having the solute there, you're going to have little blocks, and it will keep things from evaporating, and it will lower then the vapor pressure. So, yeah. So pure water will have lots of things hitting. Here you have some of the surface is blocked by the solute, so the effect of the particles pushing down will be less. Now, because of that, you get a couple different processes or situations happen. First off, in terms of boiling point will actually get higher in an impure substance than in a pure substance. So for example, if you put salt into water, it actually causes the water to have to get to a higher temperature to boil. And if you kind of think about it, some of the particles, they're all zipping around here, and some of the particles will be, not in contact with the surface. They'll hit like a solute particle and bounce back and not be able to escape until you get to, a higher temperature and more kinetic energy there until it's able to escape. So in order to boil, essentially molecules have to have enough energy to overcome the intermolecular forces to enter the gaseous phase. And like I said, solutions have a higher boiling point than pure solvent. Now, interestingly, it's inverse for freezing point depression. So with freezing point, particles don't have enough energy to overcome the intermolecular forces and form a structured solid state. So when you have a solution, it actually has to have a lower freezing point than a pure solvent in order to freeze if it is impure and it has some additive in there like NaCl. So if you have a pure substance, you don't basically have any hindrance for things like for water hydrogen bonds forming and a crystal structure appearing. If, however, you have some solute particles mixed in, those kind of get in the way of the hydrogen bonds and make it harder for this crystal of ice to form. So they're kind of blocking things and interfering, so it's harder, and things have to slow down more until the water is able to bond to itself or attach to itself with hydrogen bonds with these other things in the way. So kind of an inverse thing. If it's boiling, you actually have to get to a higher temperature to boil. If it's freezing, you actually have to lower the temperature cooler for substances to freeze. So you can remember this with the gator. And when gators open their mouth, it goes like this. So the boiling point goes up and the freezing point goes down because of impure substances such as salt water. Now, the other thing I wanted to talk about in this was something called a phase diagram. And what the phase diagram does is it shows the relationship between temperature and pressure and then states of matter. And it's saying that if something has very, very low temperature and some amount of pressure there, substances will generally be solid. So for example, ice with water. If you increase the temperature, eventually you pass the melting point or freezing point and the substance becomes liquid, such as water. If you continue to increase the temperature, at some point it will pass into the gaseous phase there. So, if this was 1 atmosphere pressure, which is, what's found at sea level roughly, at a very cold temperature, ice is, water is ice. At a certain temperature, about 0 degrees Celsius, you get enough kinetic energy to break enough of those hydrogen bonds for the water to liquefy. And then when we get to 100 degrees Celsius, you break enough hydrogen bonds that the molecules start flinging off into, into the air, and you get a gas. Okay. Well, if you lower the pressure, notice that the amount of energy it takes to form a gas is less. And that's kind of because the vapor pressure, as you're lowering the pressure pushing down on the substance is less, so it's easier for a substance to escape. Which you might have heard that, in space, if you were to go into space, there's comments of, oh, your blood is going to boil. And the idea there is that with no pressure holding things in, it just, the particles start releasing. And even at a very cold temperature, it releases or, effectively boils. So we get this kind of Y shape to it, where at low pressures, you tend to have a gaseous phase for things. At slightly higher pressures, but very cold temperatures, you'll have a solid. And kind of in the middle here with fairly, significant pressure and moderate temperatures, you'll get a liquid for substances. So most substances will display this kind of Y form to them. And again, the left side of the Y will be solid or ice. In between the two prongs of the Y will be liquid, and then below to the right will be gas. Okay, and the point where they all come together is known as the triple point. And that's kind of a cool, intellectually cool point, because at that exact temperature and pressure, you can have gas and liquid and solid all stable and not going from one to the other. Okay, so this would be a phase diagram for CO2 or carbon dioxide. And notice that the triple point for carbon dioxide is at 5.11 atmospheres. At 1 atmosphere, liquids are up here. At 1 atmosphere, if you increase the temperature, you go directly from a solid to vapor. And that's why dry ice doesn't melt. It just sublimates in normal atmospheric pressure because it just goes like that. Oops, I went backwards. Or no, yeah. Okay, so it goes up here and again, it goes directly from a solid to vapor. Okay, the last one is just to show what happens when you have that boiling point elevation or freezing point depression. Essentially, the line for boiling point will shift to the right, which means it requires a higher temperature to boil. So if you imagine, normal conditions, it boils here. But if you put a lot of solute in, it would have to get all the way out to there to boil. Okay, freezing point, again, is reversed. So instead of freezing at this temperature, it shifts over to here, and it will be at a colder temperature that it will freeze. So you see this displacement of these two lines. The right line, basically the boiling point, it will require higher temperatures to boil. The freezing point, it will be shifted to the left. It will require lower temperatures to boil. Okay, so that was that.